All right, let's talk a little bit about equilibrium and reversible reactions. Reversible reactions do not go to completion. They can occur in either direction. So our choice of reactants and products is, in most cases, somewhat arbitrary. So if we have some A reacting with B to produce C and D, the difference between that normal reaction is we tend to write it with double arrows instead of a single arrow, indicating the reaction can go both directions. And many of those reactions will go on to form a chemical equilibrium. That exists when two opposing reactions occur simultaneously at the same rate. That is, the reactants form products, and the products react again to reform the reactants, and the cycle continues. And so eventually the forward rate will equal the reverse rate, and the reaction will stop. And that point, we say we've reached chemical equilibrium or a dynamic equilibrium. The molecules are continuously reacting even though the concentration doesn't change at all. We can look at that graphically for the forward and the reverse reactions. And so if we look at that reaction of A and B reacting to form C and D, where the x-axis is time and the y-axis is the concentrations, you can see the concentrations in A and B start high and they end up becoming diminished. And then the C and D are the products. They begin to grow in because I didn't start with any of that. And they will plateau out at a maximum value. Where you see that dashed line, the equilibrium is established, meaning that now the forward and the reverse rates of the reaction are the same, at which point the concentrations won't change as long as the equilibrium is not disturbed. And so if we look at a more concrete reaction, one of the fundamental ideas is that equilibrium can be established from the forward or the reverse reaction. If we consider the reaction 2SO2 plus O2 reacting to form 2SO3, but we see the double-headed arrows indicating a reversible reaction or an equilibrium. And so if we look at this graphically speaking, we could start with SO2 and O2 and then allow the SO3 to go in. And that's exactly what this graph shows, is that the SO2 and the O2 diminish to a certain concentration, and the SO3 will increase from 0 to a concentration over time. If we start with SO3, the reaction would just go in the reverse way, and the SO2 and the O2 will grow in and the SO3 will diminish. And there's nothing wrong with either way because you can approach equilibrium from any direction. We could have just as easily started with a mixture of all the things and figured out an equilibrium as well. So for a simple one-step equilibrium, which is what we're mainly going to deal with, where A plus B is an equilibrium with C and D, where the uppercase letters are the reactants, the lowercase letters are the coefficients. We say the rate of the forward reaction is equal to the rate constant of the forward reaction times the concentration in A and B. The rate of the reverse reaction is equal to the rate constant of the reverse reaction times C and D. So for that general reaction, we say that we're at equilibrium when those rates are equal. And so if we get to that point, we can define a constant called the equilibrium constant. This is based on molar concentration. We'll talk about other systems in another video. But we have the concentration of the products over the concentration of the reactants, where the exponents are the stoichiometric coefficients of each reactant and product, which gives us a functional form for the equilibrium constant, but it will be different for every reaction. And so we have to write it differently. Concentrations, again, moles per liter. So this brings us to our example. Let's say we write an equilibrium constant expression for each of the following reactions at 500. So we got PCl5 going to PCl3 and Cl2, everything's a gas. And so we're going to look at that and see what happens. And so what we're going to do is our Kc then would be equal to the concentration of our products. So it's going to be PCl3, concentration of Cl2. All the coefficients are 1 in this one, so we don't need any exponents. And then the PCl5 on the bottom. And that would be the equilibrium constant expression, but you have to write it based on the reaction that you're looking at. Now we'll follow up and we'll actually do some work with this particular equation, and then we'll come back and write maybe a couple more. So if we look at an example involving that same reaction, we got a 1 liter container, and it was found to contain 0.172 moles of phosphorus trichloride, 0.086 moles of chlorine, and 0.028 moles of phosphorus pentachloride. We can get the concentrations quite easily since it's 1 liter. It'll just be the same thing. So the PCl3 will be 0.172 moles per liter or molar. The chlorine will be equal to 0.086 molar, and the phosphorus pentachloride is 0.028 molar. And so if these are the concentrations at equilibrium, we can then use those to calculate the equilibrium constants. You need to plug equilibrium concentrations into an equilibrium constant expression if you want to get the correct value. So remember, those concentrations have to be at equilibrium. So let's plug that in. So we're going to plug in, so Kc would then be 0.086 molar, and then PCl3 is 0.172 molar. Then we divide through by the PCl5, 0.028 molar. By convention, equilibrium constants are not given with units, even though you can see that the units would not cancel. So if we run that through our calculator, 0.086 times 0.172 divided by 0.028, and we get an equilibrium constant of 0.5. We got 2 sig figs, so we'll go with 2 sig figs, 0.53. And so that would be our equilibrium constant. All right, let's say we look at PCl5 at some new temperature, new situation, so the equilibrium constant will be different at the new temperature because equilibrium constants are temperature dependent. So, but in this case, we just put in 1 mole of PCl5 into a 1 liter container. So we're talking about a 1 molar concentration. And so there was no PCl3 or Cl2 present initially. But at equilibrium, we say that we have 0.6 moles of PCl3. So 0.60 molar. What would be the new equilibrium constant? Now that'll take a little bit of figuring, and we'll introduce a concept called the ice table. Leave enough room there to plug in my answer, but beneath that, I'm going to create an ice table. So PCl5 concentration, PCl3 concentration, Cl2 concentration. Now we're going to look at the initial amounts, how much it changes, and what it is at equilibrium. That's why we call it ice, because if you read that across, it says ICE. So initially we said that this concentration was 1 molar. And I put square brackets, so we'll assume everything's molar concentrations. As long as the volume doesn't change, I can subtract the concentrations, and we're trapping it in a 1 liter container. And we didn't have any of those, but it says at equilibrium, I end up with 0.60 molar that, which means I gained that much. Since the stoichiometry is all 1-to-1, that means I also gained that much chlorine. And then, so again, the coefficients are all 1-to-1, because if I rewind to my reaction up here, everything's 1-to-1 stoichiometry, still working with the same reaction, new temperature. So, but in this case, it's a reactant, so we're going to lose that 0.60. Reactants, if products are gaining, reactants are losing to get to equilibrium. So we'd have 0.40. And so then we plug that in, we get 0.60 times 0.60, or 0.60 squared divided by 0.40. And then you're just going to run that through your calculator. 0.6 squared divided by 0.4. And we're going to say 0.90 would be the new equilibrium constant. Again, varying with temperature. The bigger the equilibrium constant, if you notice, products are in the numerator, reactants in the denominator. So the bigger this number gets, the more product favor the reaction is. If you compare it to the answer in the previous question, this reaction is more product favored than that at the new temperature. Okay, let's look at a couple more equilibrium. We're just going to write the equilibrium constant expressions for each of these, because we need to practice with ones where the coefficients aren't all 1 like it was in the prior example. So our Kc products, so concentration of N2O4 divided by concentration of NO2, because that's my reactant. This has a 2 coefficient, so we're going to square it. And so we're going to write a 2 there, and it's going to be squared. And so that would be the equilibrium constant expression for that particular reaction. Let's look at this one. Kc, so products, going to be concentration of NH3. There's a 2 coefficient, so quantity squared divided by concentration of N2. Coefficient's only 1, so no exponent. And then we're going to have H2, and there's a 3 there, so we're going to say cubed. And so NH3 squared divided by concentration N2, concentration H2 cubed. Lastly, we got HI, so HI is the product, 2 coefficients, so it's squared. And then both these reactants only have 1 for the coefficient, so no exponent, so we just write them in brackets. So Kc is HI squared divided by concentration I2 and H2.